Hi folks, this is a multi-part series on the internet-based financial services case. In this module we'll do something a little different. Our novice problem is going to be a case that you need to write up in the form of a simulation, a Monte Carlo simulation. You bring all of your skills that you've earned up to this point to bear on this problem, and it should lead to hopefully a very nice result. We have an interesting problem here where we're interested in service capacity. That is the ability to provide someone to listen to a customer or a client, and then either make comments, provide information, or to pass on to another individual. So this type of problem exists often in the service industry, and of course in an industry like financial services where things are relatively easy to replicate. Service is very important. The service level, the percentage of time that there is availability of someone to deal with an individual will either make or break an organization. So we've got a lot of information in this problem. We've got 3 different types of customers: curious, obsessive, and all business, and there's a probability for each. Also, there's a corresponding probability distribution for the times for each one of these types of customers, and we provide that in terms of a normal distribution. You can see that the curious have a normal distribution with a mean of 7, standard deviation of 1.5. The obsessive, 19 is their average. They take a lot more time. All business people dispatch their business quickly, so their average time is 4 with a standard deviation of 1. We're also going to have some of these customers that are going to come in at lunchtime and want service that are going to need further service from the owner of this organization. And we need to take a certain percentage of the people that call in and say, you'll be one of the folks that requires more attention from the owner and manager of the business. So we'll also incorporate that into our model. One last wrinkle is that we also add the possibility that we have a day where the market is very volatile and thereby requires a higher average arrival rate from 5 to 7. The average arrival rate now should be a familiar characteristic. That's the lambda, or the average arrival time, in our Poisson distribution. So we'll need 2 distributions, one for a rate of 7 and one for a rate of 5. And we have corresponding probabilities of what is typical and what is atypical. Atypical would be when we have a lot of volatility and we need an average arrival rate of 7, and typical 77% of the time when the rate is 5. Let's quickly take a look at some back of the envelope calculations that I've done here, just to help me verify my model when I'm done. I'm going to deterministically try to determine the expected amount of time that a typical customer or client will require. A typical customer is 10% curious, 25% obsessive, and 65% all business. If I multiply those probabilities times the mean of the distribution of times for each one of these categories, 0.1 times 7, which is the mean time for someone that's curious, 0.25 times 19, 25% of my clients are obsessive, and they require an average of 19 minutes, so on and so forth. I get a typical call of this conglomerate of obsessive, curious, and all business requires about 8.5 minutes of time. If my expected number of arrivals, my average arrival rate is 5, then I'm going to have 8.055 times, which leads to a average time per hour of service, my lunchtime hour, of 40 minutes and 25 seconds. So if I do my simulation and for typical times and I don't get a number close to this, I'm going to have to look very carefully at my simulation to see if I did everything correctly. Now, we also talk about the possibility that things won't be typical with 5 units of, or 5 arrivals, average arrivals. It might be 7. That happens 77% of the time with 5 arrivals and 23% of the time with 7 arrivals. And then so therefore I can calculate the amount of time that's attributable to days that are typical and atypical. I get these two numbers by multiplying them times 8.5 times 5 times 0.77, and then similarly for the atypical time, and I get 43 minutes, almost 44 minutes of time for the combination of typical and atypical. You'd expect that because some of this time goes above 5. Before we had 40.5, I believe, 25. So now that we've added in some atypical time, we're going to get something higher. One last thing I want to talk about before I present the remainder in another part is the brain. Our brain consists of all of the values that are important to us in the analysis. The only thing we haven't talked about is the beta distribution and the individuals that are going to need personal attention as a result of that beta distribution. We've used an alpha of 11 and a beta of 0.23. We saw how in the footnote in that case it showed us that that would approximately be how we could determine the approximate values of alpha and beta from a sample size with a known number of individuals that needed attention in that sample. That gives us an average of about 32.35% of the individuals during the course of an hour will need added attention. So about a third will need added attention. All right, everything else that you see in the brain is what we've seen before. Here are probabilities, our types of customers, cumulative probability. We're going to be sampling from this discrete distribution. We're going to need these values for the probability mean and standard deviation for our normal distribution for call times. And then finally, we have another discrete distribution over here for atypical and typical days. That ends the first part of this discussion of the internet-based financial tools.